Hello everybody, my name is Angus McBride and I'm going to present to you today something very different from everything else at the EHF. It's a tool for water network modelling. It's something that's been born out of my own trials and tribulations and testing many different ways of modelling networks in many different emergency settings, and finally I think I've come up with something that could be more generally useful, both to people like me working within NGOs, but also engineers working with water utilities, particularly in developing countries. Modelling of water networks is going to be absolutely crucial if you're building a network so that you can select the appropriate pipe sizes, or if you're operating and maintaining a network so that you can understand how it's working, fix any problems if there are any, optimize the operation, or plan any extensions. In general, you're going to have two options for your software that you might use for generating the water network model. One is free software. The most famous example of this is EPINET, which was developed by the US Environmental Protection Agency more than 20 years ago. It's a great piece of software, gives very accurate, reliable hydraulic models, but it is, I would say, showing its age, and it's very difficult to get data into it and then back out of it. So when I'm talking about data in, I would be thinking of things like adding elevations to all of the nodes, or adding pipe lengths to all of the pipes and having it laid out on the earth rather than just conceptually. And then once you've done your model, once you're happy with it, once you're trying to get your results out, you're very limited in how you can do that as well. These problems don't exist in commercial software, for example, WaterCAD, but they can be very expensive, the licenses for these software. And even if within a project you can afford to pay the license, or you can get a consultant who has a license, the problem is that in time you may find that you will no longer have the license in future, or someone who comes to use this to run the network in future might not have a license, and that means that your data will be unusable to them. They're also very complicated and have very advanced functionality, but that can make them overly complicated for the simple cases, and it means that for a non-expert user, someone who doesn't use it all the time, they can be more prone to making errors with them. So what's the solution that I'm proposing? Well, it's to integrate that great functionality from EPINET with the open source software QGIS. EPINET, as I've just explained, is a recognized standard for hydraulic modeling. Its IMP file format is used, or at least exchangeable with just about any hydraulic software that exists. It can do advanced analysis, but even the basic analysis, it's rock solid and thoroughly tested. QGIS is an open source GIS program. You'll probably either know how to use it yourself or have seen other people using it in emergency responses. It's simple to use, but does have advanced features available. And one of the great things about it is it accepts a huge variety of different types of data sources. So, introducing Winter QGIS. Yes, I'm aware the name is doesn't roll off the tongue, but if anyone has a better idea, I'm listening. It's an open source piece of software, which means it's free for everybody, and that it always will be. It also means that if you want to, or if you have the knowledge, you can go and look at the source code and propose any changes. It focuses on having a very limited set of features within the plugin, but it means that each of these features is very well tested and very reliable, with over 300 tests running on every single change that's made to the plugin. And it's also multilingual, so it's in French, English, Arabic, Italian, Spanish, Portuguese, Dutch, and thanks to the power of AI, it's actually relatively easy to add new languages. And whilst the plugin itself has relatively limited features, because it's within QGIS, it means that you can use all the power of QGIS. For example, to add heights to nodes automatically from survey or satellite data. When you're laying out your pipes, you can do it on a background of OpenStreetMap or drone data, data from AutoCAD, whatever you have. And you can use QGIS for presenting the results and even creating drawings. And because the hydraulic modeling is done with EpiNet, you have that certainty, the reliability of the hydraulic results. You can do advanced modeling, such as extended period simulation or other functions, and it uses the interoperable .imp file format, so you can export your results, export your models from Winter to other programs, or vice versa. Okay, so we're going to go for a simple example here of how you might build a model from scratch. We're going to use Geneva as an example, as that's where we're at, and we're going to try and model the Geneva fountain. So I've loaded an OpenStreetMap background. We'll create a new set of layers for our model. So there we go, we have tanks, reservoirs, valves, pumps, pipes, and nodes. We're going to start with a node to model the fountain. It's at 0 meters elevation, that's fine. We'll need a lot of water for our fountain, so we're going to go for 100 litres per second. We're going to create our water tower at the train station. This is going to need to be pretty high to supply this fountain, because we're just going to do it by gravity. So that's 200 meters of elevation for the water tower. And then we're going to need to link these two with a pipe. It just needs to be approximate. At the ends, the pipe will just snap to the nearest object, so we don't need to get it too exact, as you can see. It's a lot of water, so we're going to need a big pipe. We'll make it 200 millimeters. We're not going to put in the length, that's going to be calculated automatically, although we could override it if we wanted to. And for the roughness, we'll use Hayes and Williams, we'll keep that at 100. It's about right. There we go, our model's set up. So we're just going to check our options. Hayes and Williams, that's what we want. Units, litres per second, that's what we want. Duration, single period simulation, that is what we want. Something nice and simple. Going to run it. Now if we had lots of pipes, they would come in different colours according to the properties, same with the nodes, but we don't, so we'll just have a look at our one pipe and see the results. Flow rate 100 litres per second, that's what we were expecting. Head loss 75 meters per kilometre. Velocity 3 meters per second, so that's quite a high head loss. Let's see if we've got any pressure left at our fountain, and we do. We've got 50 meters of head and pressure, so we'll have a modest fountain. Excellent. And just to demonstrate that we can do more than model one single pipe, we're going to load an example that comes with the plugin, which we've switched over to English. We'll just click load example, and it's going to load an example from Kentucky. It's a real town in Kentucky, a real network. So we can see there's reservoirs, there's pumps, there's tanks, there's lots of nodes, and we can run that as before. This one is in Hayes and Williams, and this one is in gallons per minute. So when we run it, we can see how the pipes are coloured according to the velocity, although we could change that so they're coloured according to different parameters if we wanted, and also how the nodes are coloured according to their pressure. Okay, that's it. Thanks for listening. If you would like to find out more, you can scan this QR code and it'll take you straight to the documentation site, and you can read more about how it works. Or if you already use QGIS, you can find the plugin already within the plugins menu, So please do test it out and tell me how it goes. I'd love to hear your feedback.